Hello, I'm Ewan. This is a presentation on faster isomorphism testing of p-groups of Frattini class 2. This is a joint work with Gabor Ivanyosh, Yuming Chao, Xiaori Sun, and Xuanqi Zhang. And this is also based on work published in Fox 2024. So here we're talking about the finite group isomorphism problem, which asks, given the Cayley tables of two finite groups, determine if they're isomorphic or not. And here we're only considering groups where the input is the Cayley table, so the finite groups. This problem has been widely studied in theoretical computer science since the 70s. The first algorithm attributed to Tajian was already quasi-polynomial time in the group order. And the best known improvement to this only improves this constant in front of the log n to 1/4, which is due to Rosenbaum in 2013. So group isomorphism in sub-quasi-polynomial time, or n to the little o log n time, is still an open question. And p-groups are widely thought by the experts to be the hardest cases of group isomorphism. One reason for this is a work by Heiko Dietrich and James Wilson, which showed that for most group orders, group isomorphism is nearly linear time. That is, so p groups would be order p to the k, and they're also quasi-polynomial time. So the fact that we have these p to the k order groups in quasi-polynomial time, while the most orders group isomorphism is nearly linear time, suggests that these p to the k order groups are one of the hardest cases. We also have work due to Higman in the 60s, and also work on the enumeration of the finite groups, which suggests that p-groups are the hardest case of group. And even the p-groups close to abelian seem hard, namely the p-groups of class 2 exponent p. We also have this brute force upper bound for this class of groups, which is quasi-polynomial time. And in 2023, Xiaori Sun presented the first sub-quasi-polynomial time algorithm for this class of groups, which was a breakthrough in the field. And group isomorphism also relates to graph isomorphism. That's because group isomorphism is reducible to the graph isomorphism problem. There also have also been studied since the 70s. However, interestingly, compared to group isomorphism, graph isomorphism is considered solved in practice. So we've got Babai, Erdos, and Shelko's average case algorithm from the 80s, and McKay's practical algorithm from the 80s. And also, while compared to group isomorphism, graph isomorphism started off as an exponential time bound, there was a lot of significant progress made on this bound, culminating in Babai's quasi-polynomial time breakthrough in 2017. And graph isomorphism, the quasi-polynomial time algorithm for graph isomorphism can't be used to improve the group isomorphism algorithms. And so this suggests that group isomorphism is a roadblock for putting graph isomorphism in P. And specifically this class of groups, because they're the hardest case of group isomorphism, or thought to be the hardest case of group isomorphism, is a roadblock to putting graph isomorphism in P. So Sun's result from 2023 says that for odd p, given two p-groups of class 2 exponent p and of order n, there exists an algorithm in time n to the o log n to the 5/6 that decides whether they are isomorphic or not. Our improvements is both generalizing the class of group and asymptotically improving the running time. So our main theorem is given odd p and two p-groups of Frattini class 2 of order n, there exists an algorithm in time n to the o tilde log n to the half that decides whether they're isomorphic or not. In order to do this, we need to make some nice correspondences between three tensors and p groups of Frattini class 2, which we can use the work of Bayer, Higman, and Grochow-Qiao to do. In our setting, what we mean by a D-tensor is a D-way array, and a 2-tensor is a matrix, and a 3-tensor is a tuple of matrices. We also have these actions of invertible matrices acting on each side, so L will do row operations on a matrix, and the matrix that acts on the left will do linear combinations of the horizontal matrix slices here. And similarly, we'll have an R multiplying on the right, which will do column operations, but R multiplying on the right here will do operations on these vertical matrix slices. And we also have this implicit third direction of T, which will do linear combinations on these frontal matrix slices here. And then we also have a corresponding isomorphism problem for this 3 tensors. So let's say given 2 tuples of matrices, then there exists, then the tensor isomorphism testing problem asks whether there exists invertible matrices L, R, and T, where L and R will multiply on the left and right of the tuple, and the T will do linear combinations in the third direction. And if we consider this A and this B as an ordered basis of a matrix space, then it also encodes the matrix space, because this A and this ordered basis B will span the space. So, as previously described, we have this Bayer and Higman reduction from p groups of Frattini class 2. And this will reduce to alternating matrix space equivalence, which we can reduce from that problem to the tensor isomorphism problem, which is due to Grochow-Qiao. And remember, and this is possible because this third direction encodes the span of the matrix space. So this third direction doing linear combinations, so the tensor acting on the third direction doing linear combinations will give us an equivalence problem for matrix spaces. And it also gives us that if we have 2 p groups of Frattini class 2 of order n, and this can be tested in n to the log n to the c time, then this will be polynomial time equivalent to 3 n by n by n tensor isomorphism testing over finite fields of order q and q to the O n to the 1 plus c time. This also gives us a natural brute force upper bound by enumerating all the invertible matrices. And Sun's result in the multilinear tensor setting will give us a q to the O n to the 1.8 log q time algorithm for this problem. And our main theorem will now become, given 2 3 tensors, there exists an algorithm in time q to the O tilde n to the 1.5 that decides whether these 2 tensors are isomorphic or not. So, how this algorithm actually works, let's say we have 2 p groups and they encode ordered basis which span this matrix space, and we want to find L, R, and U, which will send these 2 matrix spaces. L, R, U will send the matrix space A to B. Then we can reduce this to the congruence testing of matrix tuples, which is solvable in polynomial time by Ivanyosh and Chow in 2019. What this looks like is we need to somehow fix this third direction so there's no U which does linear combinations on the frontal slices. It's also convenient to reduce this to the congruence testing problem. So instead of asking whether there's a left and right matrix, we're asking whether there's a T transpose and T acting on the left, right, or the congruence action. We also have, so in order to make this reduction, we introduced an intermediate object, which we call the semi-canonical tensor, as this bridge between the tensors and tuples. What this looks like is we have this canonical block structure here, where we have this large zero block and these small canonical matrices in the margin. Then in this third direction, we have this relatively large structure, but is fixed in some canonical order. So how we actually construct this semi-canonical tensor? First, we need to introduce a parameter S, which is small compared to n, and we'll consider the matrix space, which is spanned by this by the frontal slices of the tensor. Then we can randomly choose left and right multiplying matrices, where we have an S by n matrix multiplying on the left, an R by S, an N by S matrix acting on multiplying on the right. And what L and R do is they compress this matrix space to this smaller space. And so we'll get this image space where the space spans these compressed matrices. And in the kernel space, we get essentially the information lost after multiplying left and right matrices. So L and R will send A to 0 in the kernel space. So in the actual algorithm, we can set this parameter S to be O square root of n, and by change of basis matrices, we can set this kernel space to span the frontal slices of the tensor. And then the remaining slices will span the quotient space. Will consist of the quotient space here. And we say that this image space can be, a canonical basis for this image space can be computed efficiently. Then, using this canonical basis for this image space, we can use this image space as labels to sort the matrices or fix the matrices in this quotient space here. And we introduce this result that gives us, because now we have this kernel space that's not fixed in any canonical order, but we can use this property that this kernel space has a rank bounded by a square root of n. And so how do we actually know that we have this rank bounded by square root of n? We introduce this lemma. So if we fix this parameter S, which is this the size, so which corresponds to the size of the left and right multiplying matrices, then we can get with high probability a rank bounded by R in the kernel space. So we can set the target rank to be square root of n, because we want this rank to be small compared to n. And we can also get, using the lemma from before, we'll get square root of n to be, s to be square root of n. And if we sample enough times, eventually we'll get a matrix space where the kernel has a low rank. And to deal with this low rank space, we can put it in this following structure. We can get this large zero block here, this large canonical zero block, and then we can get these small margins in compared to n. and we want these margins to be canonical. So how we do this is say that you have left multiplying and right multiplying matrices L and R and a matrix of rank R. Then say by Gaussian elimination, for example, you could find this large zero block and these margins. A similar result in the 3 tensor or the matrix space setting is from Flanders that says that if we have these if we have a rank or a matrix space of rank bounded by R and over large fields, then this D and F part will be O of R, or upper bounded by R. So Sun improves this lemma to any arbitrary field, but then he improves it so that this D and F will be R squared. So if we have a matrix space rank bounded by R, then the D and F part will be upper bounded by R squared. So our improvement gets this to a tighter bound of R log R. We can also find this structure, we can also canonicalize this structure efficiently due to Grochow-Qiao and Subramanian. And the key technique that we use to get this canonical structure relies on this idea of non-commutative rank. So non-commutative rank I'll talk about a little bit later, but how this actually fits into the running time of the algorithm is, say that we have this n by n by n matrix, or this n by n by k kernel space, and this kernel space is rank bounded by R, and we know that this R is square root of n. Then using this lemma we can just plug in square root of n and get this D and F structures will be, this D and F margins will be size square root of n log n. And yeah, so these D and F structures will be at most O tilde square root of n. So actually, to introduce the notion of the non-commutative rank, let's consider this subspace of f of n and this matrix space where after applying A will send the subspace as below. Then we say that U is a G-shrunk subspace of A if the dimension of U minus the dimension of the image of A under U is greater than G. So in this sense we can think of U as sort of a matrix where A shrinks this subspace and gives it a large zero block. Then this non-commutative rank is n minus the largest G-shrunk subspace of A. And this is an interesting topic that's been studied by Gar, Gurvitz, Oliveira, Widgerson in 2020, and Hamada and Harai in 2021. And this can be done in deterministic polynomial time. But more useful to our algorithm is that we can actually compute a canonical G-shrunk subspace by Grochow-Qiao and Subramanian in 2018. So now that we have this canonical structure, let's consider the matrices P, Q, and S acting on the three directions of the semi-canonical tensor. This P, Q, and S will have to respect the canonical structures of this tensor. So after some enumeration, this P, Q, and S will look like the following structure, and we can see, if we think carefully, that each of these block matrices will only act on the canonical structures in two directions. So if we take these matrices from the canonical structures and place them into the tuples in the following way, then we can take these P and S matrices here and construct a following invertible matrix out of these matrices. And essentially this gives you that if you have P, Q, and S acting on three directions of the semi-canonical tensor, then this semi-canonical tensor will be isomorphic if and only if the corresponding instance of matrix tuple congruence that we've constructed is also, if the corresponding matrix tuples are congruent. So in summary, we found an n to the O tilde log n to the half time algorithm for groups of order n and p groups of class 2 exponent p. We've also extended this to p groups of Frattini class 2. Also interestingly, by Grochow-Qiao, this result will naturally extend to many isomorphic testing problems, such as algebra isomorphism testing and polynomial isomorphism testing, with the same time bound. We also have the following open questions. So, whether we have a sub-quasi-polynomial type algorithm for general group isomorphism of order n in finite groups is still an open question. We also have been considering the action of the general linear group across the general linear group across the general linear group on a tensor T. But what happens if we consider, say, the unitary group which acts on the tensor T, or even the orthogonal group acting on a tensor T? We also have some applications for this work. So in post-quantum cryptography, there are several protocols which relate to this tensor isomorphism testing framework, such as LESS, MEDS, and ALTEC. In quantum information, tensor isomorphism testing gives a very nice description, a nice computational description to the idea of local unitary, local operations in classical communications and stochastic local operations in classical communication equivalents. Obviously, P-group isomorphism testing is an interesting problem for computational group theory, and tensor-based systems have been used in, say, practical applications such as magma and gap, practical implementations such as magma and gap, and also, interestingly, used in machine learning, such as reconstructing data from their signature paths. And thank you. That's the talk.